It is 2 a.m. A junior console operator with 6 months on the unit is monitoring a complex chemical process when a critical pressure gauge begins to drift out of bounds. In many facilities, the response at this moment depends on the intuition of experienced staff who know that the pressure usually runs around 150. But when those veterans are on vacation, the person at the desk has no technical anchor for their judgment. Safe operating limits are the singular technical concept that provides this anchor, preventing catastrophic failure when individual experience is unavailable. These limits define the exact physical boundaries of a process and dictate the specific, predetermined actions required when those boundaries are approached. A facility operating without these documented boundaries relies on the memory of its personnel, leaving the safety of the unit to the variable experience of whoever happens to be on shift. Defining these limits is a mandatory requirement under OSHA Process Safety Management and EPA Risk Management Plan regulations. The regulations require that these limits be integrated into the facility's technical documentation, its operating procedures, and its criteria for mechanical integrity. However, many facilities treat this as a paperwork exercise, creating static tables that prioritize easily documented parameters like tank levels, while ignoring critical variables like nitrogen header pressure or acid concentrations. These tables often provide vague instructions, such as notify supervisor, which offer no actionable guidance during a rapid excursion. These entries satisfy an auditor but fail to assist an operator in a crisis. For these limits to protect the plant, they must serve as the active technical basis for the unit's operation, governing how the hardware is monitored and maintained daily. A safe operating limit is part of a larger, nested envelope architecture. At the center is the normal operating envelope. This represents the day-to-day range where the process is optimized for throughput, product quality, and reliability. When a parameter reaches the boundary of this envelope, it signals a shift in conditions. This typically triggers process alarms that prompt an operator to investigate. Outside the normal range lies the troubleshooting zone. Here, the process has drifted, but it has not yet reached a point requiring emergency action. This zone requires prompt human intervention. The operator must identify the cause of the drift and return the parameter to the normal operating envelope. As long as the process remains within these green or yellow zones, the system is under the active management and correction of the human operator. The safe operating limits form the hard boundaries that encapsulate both the normal and troubleshooting zones. Reaching this threshold marks a fundamental shift. Human judgment bends, and immediate, predetermined action becomes mandatory. These actions are decided and documented in advance, such as the automatic activation of a safety instrumented system or a mechanical shutdown of the equipment. Outside the safe operating limit is the buffer zone. Its purpose is defined entirely by the timing of the process. The size of this zone provides the time necessary for the predetermined safety action to arrest the deviation before the process reaches the physical limits of the equipment. If this buffer is too small to account for the speed of the process change, the safeguards will be unable to stop the excursion before damage occurs. The final boundary is the safe design limit. This represents the absolute engineering capacity of the physical equipment. These limits are dictated by engineering codes and technical standards. They define the maximum or minimum values, such as a relief valve set point, that the hardware is designed to handle. Exceeding a safe design limit requires a formal investigation and a professional engineering assessment to confirm the integrity of the equipment before it can return to service. This nested framework is symmetrical. It applies to most parameters in both high and low directions. A vessel designed for high pressure may be vulnerable to vacuum, and a reactor that risks a runaway at height also create hazardous conditions if the temperature drops too low. This completed model reflects the physical reality of the process, providing the foundation for every safety activity in the facility. This physical architecture dictates the targets evaluated during a process hazard analysis, or PHA. The PHA team uses these boundaries to identify scenarios that could cause a deviation and determines if the current safeguards are sufficient. Operating procedures are built around these boundaries. They translate the limit values into actionable steps for the operator to take at each threshold. Alarms and interlocks are the instrumented expression of these limits. An alarm at the normal limit warns of a drift, while an interlock at the safe limit initiates protective action. Finally, the safe design limits establish the baseline acceptance criteria for mechanical integrity. These limits dictate whether equipment is still fit for continued use during inspections. Every safety protocol and inspection in the facility is an operational extension of these physical boundaries. Physical equipment degrades over time. This means the original design limits established when the unit was new do not remain permanent. Corrosion reduces the thickness of vessel walls, and prolonged thermal stress causes metallurgical changes in the steel. As the physical integrity of the hardware declines, the safe design limit must shrink inward to reflect the actual condition of the equipment. Facilities that rely on static, original design values instead of updated mechanical integrity data operate with a gap between their documented limits and physical reality. When operating limits are treated as permanent fixtures rather than living documents, the facility accumulates physical risks that are no longer captured by the original safety analysis. This gap leads to systemic drift, where the data used to run the plant becomes inconsistent across different departments. A management of change process might update a limit in the alarm database, but fail to trigger a corresponding update in operating procedures, or the PHA. These siloed updates cause safety systems to misalign, providing operators contradictory instructions or incorrect set points during an emergency. To address this, a line manager can select a single high-consequence parameter and trace it through every system in the plant. By verifying that the safe operating limit table, the alarm set point, the operator's display, and the PHA all share the same value, the manager can confirm the health of the facility's change management process. The long-term solution is a master record for each critical parameter. This serves as the single source of truth, ensuring that any change to a limit is automatically and consistently propagated to every connected system in the facility. The Safe Operating Limits framework protects a facility when these physical boundaries are accurately maintained and consistently reflected across every procedure, alarm, and technical record. Maintaining this alignment ensures that the safety systems are always anchored to the current physical reality of the plant.